In this video, we are going to be talking about work. Whenever I think about this section, I think about the Rihanna song. The term work is used in everyday language to mean the total amount of effort required to perform a task. In physics, it has a technical meaning that depends on the idea of a force. In general, we say that work is done by a force when it moves an object. The concept of work is important to scientists and engineers for determining the energy needed to perform various jobs. Now let's talk about work done by a constant force. There are many types of forces: centrifugal, electromotive, and gravitational, to name a few. A force can be thought of as a push or pull. A force changes the state of rest or state of motion of a body. We can find constant force with the formula F equals ma, where m is the object's mass and a is its acceleration. If you've ever taken a physics class, that formula should be very familiar to you. So let's define work. If an object is moved a distance d in the direction of an applied force F, then the work W done by the force is W equals force times distance or displacement. Here we have a table that will help us if we are looking at various calculations and measurements in the metric system versus the US customary system. So let's look at a few examples really quickly. If we are measuring acceleration, which we often denote with a lowercase a, in the metric system, that's often measured in meters per second squared. That's the shorthand. In the US system, we measure it in feet per second squared, and then this is the shorthand for that. If we are talking about a force, in the US customary system, we denote that or measure that with pounds, and the shorthand notation for that is lb. And force for the metric system is in newtons, and 1 newton is equal to 1 kilogram times meters per second squared. And then work, you can either measure it in newton meters or joules in the metric system, and then in the US customary system we measure it in foot-pounds. And note that 1 foot-pound is approximately 1.36 joules. Let's go ahead and jump into an example. How much work must be done in lifting a 50-pound object 4 feet? So in this one, I can just go ahead and use this formula, work equals force times distance or displacement. And in this case, our force, because it's being measured in pounds, that tells us that we are looking at a force in the US system. So I have 50 pounds times, and then 4 feet. And so 50 times 4 is 200. And then if I multiply pounds and feet together, that gives me this unit called foot-pounds, and that is how we measure work in the US system. So that concludes example 1. Example 2 says, how much work is done in lifting a 25 kilogram bag of rice off of the floor to put it on a table that is 0.8 meters high? Use that the acceleration due to gravity is 9.8 meters per second squared. So here, work is equal to the force times the distance traveled, and because we are given that the bag is 25 kilograms, that tells us that we are in the metric system, and this represents a mass. Now, the difference between the metric system and the US system here is that because we are given a mass, that is not equivalent to the force, and so we need to break up the force and use the formula that we saw earlier that says that force is equal to mass times acceleration. And then we're still multiplying by d. Oh, look at that. It spells the word mad, like as in math and physics are mad cool. So our mass is 25 kilograms. And the acceleration, it tells us to use 9.8 meters per second squared. And then the distance is 0.8 meters. And so if I multiply 25 times 9.8 times 0.8, that is going to give me 196. And then notice that here, if I have kilograms times meters per second squared, that is this. And so the highlighted portion remember this thing, mass times acceleration, represents a force, and we have kilograms times meters per second squared, which is equivalent to a Newton. And Newton, we write a shorthand with the capital letter N, and then we're multiplying by a distance that's in meters, and so that is why we have Newton meters for our work. So I'm okay with either one. You can put 196 Newton meters, or you can write J for joules. Either is fine. So now let's talk about work done by a variable force. If an object moves along a straight line but without a constant acceleration, we will have a variable force. If we call the position function of the object s of t, then the force on the object is given by Newton's second law of motion as the product of its mass and its acceleration. In other words, force equals mass times the second derivative of the position function, which in Calc 1 we would have learned that that is equivalent to acceleration. So let's look at the definition. If an object moves along a straight line from A to B by a continuously varying force f of x, we define the work as capital W equals the definite integral from A to B of f of x dx. Example 3 says a particle that moves along the x-axis by a force that measures x squared plus 3 pounds at a point x feet from the origin. Find the work done in moving the particle from the origin to a point 4 feet from the origin. So here's a visualization of what's happening. We have our x-axis here. Let's say the origin is right there at 0, and we want to know how much work is going to be needed in order to move my particle from here to, let's use a different color. So I'll start here and move it here. And so how much work would that take? Well, I have work is equal to, my limits of integration should be 0 to 4, and then my force function is x squared plus 3, and then we are integrating with respect to x. So now I just take the antiderivative, and if we simplify that, it ends up being 33 1/3. And then we're in pounds, so then the units of measurement for this would be foot-pounds. So that's our final answer for this example. Hooke's law says that the force required to compress or stretch a spring is proportional to the distance that the spring is compressed or stretched from its original length. That is, the force is equal to K times D, where the spring constant K depends on the nature of the spring. And notice that there's an asterisk, and this asterisk says that Hooke's law holds provided that the distance is not too large. So here's a visualization of what's happening. I have some frictionless surface, and my object on the spring is starting at 0, and then if I take the spring, and if it starts at 0 and ends up here at x, in order to stretch that spring, the force that's required to move it a distance of x is K times x, where K is our spring constant. And obviously the spring constant changes depending on what kind of spring you're looking at and how much it stretches or compresses and how easily it does so. So example 4 says, a spring has a natural length of 20 centimeters. A 40 Newton force is required to stretch and hold the spring to a length of 30 centimeters. How much work is done in stretching the spring from 32 centimeters to 35 centimeters? Okay, so what's happening here? Well, let's say that the natural position here is at 20 centimeters, and then I want to take this and I want to stretch that so that it is now at 30 centimeters. And in order to do that, it says it requires a 40 Newton force. Now, something that we want to be mindful of is that at the beginning of this video we talked about newtons, and Newtons require that we be working in meters when we're talking about distance or displacement. And so I'm going to go ahead and take my 20 centimeters and convert that. That is equivalent to 0.2 or 0.20 meters. And then 30 centimeters is 0.3 or 0.30 meters, like that. Actually, why don't I erase the zeros? So this is 0.2 meters and this is 0.3 meters. Okay. And what this is telling us is that, well, let's write the force function. So the force function is f of x equals our spring constant times x. So this is the force, and x represents the displacement or distance. And what I can do in that formula is I can replace the force with 40, and then k is the spring constant that we're trying to solve for. And then the displacement that it traveled, going from 20 centimeters to 30 centimeters, but remember we're talking about in meters, so the distance that it would have traveled is 0.1 meters. And if I'm solving for k, I can divide both sides by 0.1, so I get 40 over 0.1, which is equal to 400. So k equals 400, that is our spring constant. So that means that our force function is equal to, instead of k times x, we know that k is now 400, so our force function is 400x. So now I'm going to go ahead and set up my definite integral. The work required to stretch the spring from 32 centimeters to 35 centimeters. I'm going to go ahead and erase this. First off, we want to convert these to meters, so that's that. And don't forget, our natural position in this example was 0.2 meters. And so we want to think about these distances away from 0.2, because 0.2 is our natural position. So this is 0.12 meters away from natural position. And then this is 0.15 meters away from the natural position. Why do we care about that? Well, those are going to be our limits of integration. So that's why that's important. And then our force function, we said earlier, was 400x dx. And I'm just going to go ahead and tell you that if you integrate this, you should end up getting that the work required is 1.62 either joules or Newton meters. Either one is fine. And that is the end of this example.